I want to imagine a situation. Now, okay, I guess before I get too far into this, I need to get my hat because we're going to go on an exploration. Let me get my hat on. There we go. There we go. I think I'm ready for doing some exploring. Now, I want you to imagine that you're entering into a deep, dark, dangerous jungle. So suppose here's me. There's me. I'm right there. That's me. You can't really tell. It's rather round though, and it's dark. So you know it has to be me. You see my hat from, so you can look at this like a sky view. That's me wearing the hat. So what I would like to look for is what I'm going to call the Lost Temple of Awesome. So I hear they have really good gummy bears and chocolate chip cookies. So here's the Lost Temple of Awesome. See, Lost Temple of Awesome. So I'm looking for this Lost Temple of Awesome, and I see that there's some pathways I can take. So now keep in mind, I don't necessarily know how to get to the Lost Temple of Awesome. Now suppose that there's some pathways that I could potentially take to get me through this deep jungle to the Lost Temple of Awesome. But here's the catch. Here's the catch. There might be some scary jaguars out there. There might be some scary jaguars. That they always like to come out at nighttime, and poor Dan's looking for the way to get to Lost Temple of Awesome. See, this is the ferocious jaguar. And I want to avoid the lost jag. See, like they're very elusive. They're just all over the place. So we gotta be very careful not to run into the jaguar because they really bite. So me right here, I'm trying to find the Lost Temple of Awesome. We're gonna watch out for those jaguars. Now, in depth first search, now I could take a depth-wise way of exploring this jungle, right? So, for example, I could take this pathway and go as deep as far as I can along these pathways. But here's the problem. Notice that if I do that, I might take this really long pathway and uh-oh, the jaguar might be right over here. Its big pointy teeth. It might be way over there. And I don't want to go down necessarily that pathway. And what if I do? Like, the point is that I might take this really long pathway when it actually might be that it's just right here. Or just as another example, it could be the case that maybe I go exploring this way, but maybe I take this route instead. Now, suppose that I would like to explore in a different way. Instead of going depth-wise, suppose I want to explore breadth-wise. Now, what do I mean by that? So instead of taking the ball of string that I had previously, and unrolling it as I explore, and then whenever I hit a dead end or no more options I can explore, I roll it back up. Instead, I'm going to use this, and I'm going to imagine I put this like a peg into the ground, and I measure out a certain distance from the peg, it's like if I was surveying, and I look everywhere within that radius and see if I can find what I'm indeed seeking. So for example, I'll go take one step into the forest. I'll take 2 steps. I can take 3 steps in. I can take 4 steps in. I can take 5 steps in. And 6 steps in. But as I do this, I can explore more of the jungle. But I do it from my starting point, and I take steps in and I explore everything breadth-wise. So I examine these you can almost see it like I'm exploring by expanding my search out along these pathways. But I only do it a certain distance from the start. So I don't, for example, go on a long trip over here to Mochi the jaguar. I don't do that. She'll go and she'll come get me. Instead, what I would do is I would take this route. I would try to expand out my search by taking steps into the jungle, but doing it breadth-wise. That way I can look at my alternate paths, and there's a one lovely property that this approach has, is that if I'm always taking an equal number of steps in, and the distance on these paths don't really matter, meaning that it's not weighted, it's not like a true distance, it's just the number of links I can take to get to the place, I can actually minimize the length of that path using this approach. So this is actually the core idea of breadth first search, is that we, instead of it being where I just go running, be like, oh, I'm gonna go into the jungle, I try to go as deep as far as I can with my ball of string. Instead, what I do is I survey and I take steps in and I go around each time. And here's the neat part. You know how I drew this analogy of using a stack for depth first search? The thing that makes the reason why the string operates like that when we talked about solving the maze or exploring the maze, to be a bit more precise, is because the string was operating like a stack. Well, what if I want to have it so it explores all of the vertices that are 1 step away from me, then the ones that are 2 steps away from me, then the ones that are 3 steps away from me, and when I talk about steps, I'm talking about the number of edges that you use to get there. You don't use a stack, so instead of using a stack, you use a queue. So you use that in DFS. We use a queue, which is another one of these classic abstract data types or data structures. So one thing I want to point out about our exploring process is that, again, we're going to label edges, we're going to mark vertices, and again, using the same setup we had previously. But one thing I need to stress is that I'm going to label edges as 2 kinds. So we're going to still have our discovery or forward edges. But we're going to have instead what we call cross edges instead of back edges. I won't go into detail today why we call them cross edges, but the point is that they're going to facilitate a purpose very similar to the back edges. In fact, in a lot of the applications I've talked about, it would serve the exact same purpose. But the point is that when we explore a vertex, instead of it being where we imagine it almost like every time I find a new thing, I push that onto a call stack or just a stack. Instead, I'm going to enqueue it in or enter it into a queue so that those that are closer to me, they get examined first, not later. So let me do an example of what I mean by this, then we'll see what the algorithm looks like. So each time we enqueue a vertex, so each time we enqueue a vertex, we mark it so that it can be explored. So it will be explored upon being dequeued or when it leaves the queue, when it gets its turn. So you might ask, Dan, why is that really important? Why do we have to mark them before we put them into queue? Okay, so let's think about this. Suppose that you were exploring it akin to what we talked about there. Well, imagine you re-encounter the same vertex or node again. Do you want to do anything with that node at that time? No, right? We want to hang on to it for when we need to look at it at the time for which we first encountered it. So that's the other important detail here. So let's do an example here. So I'm just going to draw out a graph here. Four, 2, 5, 3, 3 to 5, 4 to 5, 6, 4, 7 to 8, 4 and 6. And we're going to need a queue. So we're going to have the front of the queue, and we're going to have the rear of the queue. So remember, in a queue, when you end queue, goes on the rear of, just think of it like you're waiting in line. You go to the back of the line, wait for your turn. When we dequeue, comes off the front. So please keep that in mind. Now, one other detail I would like to take advantage of is that I'm going to augment the representation here a little bit. I'm going to have it so that, this is more of a matter of discussion here. I'm going to have it so that we store parents, so that we could have a discussion about what underlying structure might be hiding in this thing. So each one of the nodes is going to have a parent attribute. All of them I'm just going to set to null or nil, whatever you would like to call it. It's not anything right now. That's the point. So each one of these I'm going to make its parent nil. Nil, and our parent here, I'm going to make that nil as well. This is going to be relevant later. So the point here is that we're going to have this be facilitated in a very similar way that we had before. Instead of it being a stack, however, it's going to be a queue. So as long as you understand that how waiting in a line works, that's all we have really here. So I'm going to label the edges in a way akin to what we did before. So I'm going to need my red marker, and I'm going to need a green marker. Oh, this one smells like green apples. I'm not even kidding. It's scented. But don't do that with normal whiteboard markers. That is your advice for the day. Don't huff markers. If you find out anything after this and you're like, what the heck did Dan say? Now you know why. So anyways, we're going to start off here at 1. So this is going to be where we're going to start this process. So I'm going to start off by marking 1. I put 1 into the queue. So that's what I start off with. I'm not going to do anything with its parent at this stage. I'm just going to assume it's just initially set like this. And now what I'm going to do is I'm going to ask, while this queue isn't empty, I'm going to just simply pull off. I'm going to do a dequeue. And I say, okay, well, let's look at doing something with this vertex. And I say, okay, well, if there's anything I have to do, I would do it here. Then what I do is I go through each one of my incident edges. If it's not labeled, there's two possibilities. If the other endpoint is not marked, then you know right away you have a discovery edge like we had before. And then what I do is I'm going to take this vertex 2, I'm going to NQ it, and I'm going to mark this vertex. So that when I come back to it, I know that it will be only because that was the first time I encountered it. That's an important detail. That's the first time you come into it. Come into contact with it. So next, I'm still going through my incident edges, by the way. I'm not going to go to 2 and keep exploring from there. I'm still going to go through all my incident edges. Remember, I'm going to take one step toward or one step into my graph. Remember, think of me going through the jungle, watching out for Mochi the jaguar, okay? So next, I go through my next incident edge. Notice that this one isn't marked. The opposing endpoint isn't marked. So I'm going to NQ it, 8, and I mark it. Now, I have no more incident edges to consider. So I'm done with 1. So now let's go to our next one. We're going to DQ 2. So presently we're going to process 2. Now, one thing I want to point out before we get too ahead of ourselves. To get to vertex 2, I used vertex 1, right? So I can always keep track of that information when I encounter these vertices, right? So suppose that I wanted to know which vertex I came from, its predecessor or parent. I can keep track of that information as soon as I first encounter it. So when I initially NQ'd them, I could have kept track of that information. Just a little note. So now, let's go through 2. Let's go through our incident edges. There's this one. Well, I haven't been to this vertex yet. I'm going to update its parent because, hey, look, I found it. I'm going to mark it, and I'm going to NQ it. Then next, I'm going to consider 4. Because remember, I go through all my incident edges, right? I don't proceed to the next one in the queue. So next, I found 4. Its parent is also 2. I mark it. It gets NQ'd. I go through this incident edge. Oh, look. This one's already marked, so I'm going to mark that with red here. This is what we're going to call a cross edge. So that's going to be a cross edge. There's something interesting that goes on with these cross edges that I'm not going to go too much into, but most certainly you can think about it. But notice I don't NQ 8 because we already have 8 in the queue. That's the big thing. Remember, I'm going to get to 8 eventually. But I got there when the very first time I encountered it, I used 1 edge to get there, not 2 edges. Just like in my analogy over there where we explored through the jungle, I wouldn't go back to where I originally was, right? I already looked there. So next, we're done with 2. Let's go to 8. So let's DQ 8. So 8 is presently what we're looking at here. We go through our incident edges. Those are labeled. Okay, we got this one here. Okay, cross edge or discovery edge. Well, it's already marked, so we know we aren't going to do anything interesting with that. This right here, that isn't marked, so we're going to most certainly we have a discovery edge. We're going to update its parent to be 8. We're going to mark it, and we're going to NQ7 into the queue. And now I've looked at all my incident edges. We're done with 8. Is that nice? So now, so far, we've gone through 8. Now next, we've got 3. So let's DQ 3. Let's look at our incident edges. We have one right here that is not yet been examined. Its opposing endpoint is not marked, so we're going to mark it. We're going to update its parent to be 3 because that's the opposing endpoint here. And I'm going to NQ that in there. And that's all the incident edges for 3. Let's consider 4. We're going to DQ 4. That's labeled. That's not labeled. But this is already marked, so I'm going to label it as a cross edge. And then that's, well, I haven't been to that one yet, so let's go there. Well, I'm going to hang on to it for later, so I'm going to update its parent to be 4. So 6 is going to go in here. I've already marked it just now. here I've already been there, so I'm going to label this as a what kind of edge? Forward edge or cross edge? A cross edge, right? And now we're done with 4. Now we DQ 7. Well, this is the only incident edge that has not been labeled yet. Is this discovery or a cross edge? It's a cross edge because this is already marked. And we're done with 7. Next we got 5. Nothing interesting happening. All the incident edges are already labeled. Same thing with 6. And we're done. We've processed all the edges and vertices that are reachable from the start vertex. One thing you might ask is, Dan, why did you label all of these parents? Now suppose, just for the hypothetical reason, that you wanted to say compute a path. And I must stress, the reason why I'm also showing you this is that if ever you wanted to adapt, say, depth first search, and you wanted to use an iterative approach there, you can also adapt something very similar to this, where you hang on to parents like this, so that if you needed to get any one of the pathways, you could follow these parents. So for example, suppose that I wanted to get a path from 1 to 5. Well, notice that I could just follow the parents from T. So suppose I did run into T. I could just simply adapt to what I talked about previously in our applications of depth first search, and you'd use the same idea. So you just simply update the parent. So you just have a loop where you just check while the parent is null. It's not null. You just follow each one of the parents. It tells you where to go, and you eventually get back to S. So that's why I wanted to show you this. It's an interesting curiosity, but this is also a nice idea if ever you wanted to, say, compute a pathway. But yeah, no, so this is the idea behind breadth first search, is we always take in 1 step, 2 steps, 3 steps, 4 steps. In fact, I'll show you right now what I mean by this. So let me just get these markers put away here. Sorry, I'm getting really excited here. Okay, I'm just getting covered in green apple whiteboard marker. Okay, I'm going to show you something that's interesting that's going on here. Now, where did I stick that blue marker? That's not the blue marker. It's gone. But anyways, let me show you something fascinating. So watch this. Do you remember how this worked? Because of the way we employed the queue, I want to show you how Dan's exploration to the Lost Temple of Awesome, when I take 1 step, 2 steps, 3 steps, 4 steps, is exactly what's happening over here. Except not literally. So notice that when I start off at S, I use 0 edges to get to S, right? So we would call this level 0 or layer 0 in a breadth first search. Notice that I used 1 edge to get to 2 and 8 like this. We would call this level 1 or layer 1. So we'd call these layers or even levels. Usually levels is more common terminology. Now, when you go from, say when we started exploring from 2, notice that the order, because of the way we use our queue, notice that the number of edges to get from 3 to 1 is exactly 2. Number of edges to go from 4 to 1 is exactly 2. And the number of edges to go from 7 to 1 is exactly 2. So we call that level 2 or layer 2. And these are the ones that take 3 edges to get to. So this would be called L3, layer 3, level 3, whatever you'd like to call it. So when we do a breadth by search, what's actually happening is it's just like what I said when we went out into the jungle where we're looking for the ferocious Mochi the jaguar, okay? So we take 1 step in, then 2 steps in, then 3 steps in, but notice that the queue facilitates that we take in 1 step, then 2 steps, then 3 steps. One neat property about this that I'm not going to prove here is that when you look at this, as we've talked about briefly when we talked about depth first search, a lovely person had put it out in the chat, is that you end up with a spanning tree if this is in fact connected. So those green edges, the discovery edges, again, like in depth first search, will form a spanning tree. But here's the neat part about breadth first search. If I wanted to find an ST path, akin to something we talked about in the past, using breadth first search, however, this tree that we've constructed, which is called a breadth first search tree, by the way, this tree has a very nice property. Because of the way we explore level by level like this, the levels in the tree actually tell you how many edges you need to reach a vertex at minimum. So these dictates actually shortest ST paths. So for example, if I want to get the shortest path from S to T over there, I need at least 3 edges to get there, and this is one such shortest path. So this is one benefit that breadth first search has, is that it gives you what we call a shortest path tree in an unweighted graph. Another way you can think of this is if your graph had weights for the distances, like these actually were distances, you can imagine this as if all of the weights were the exact same on every one of the edges. You can use breadth first search like this to compute shortest ST paths. Pretty fascinating stuff. But that's a property of the breadth first search tree. Depth first search also has a tree like this, but it's not the same structure. You can't claim that it computes shortest paths. But breadth first search trees most certainly have this property. So I thought I would, let's talk about the algorithm now. Let's put this all together now. So now we have the idea of what breadth first search is and how the exploration breadth-wise operates. Now we got that, so let's talk about and describe this in pseudocode. And then we'll do the analysis. So algorithm, we're gonna have the same setup that we had before. BFS, we're gonna have a starting vertex. We're gonna have a vertex U of the set of vertices of a graph G is equal to VE. And for output, we're going to have what we call a breadth first search traversal. What we did over there is what we call a breadth first search traversal. So we're going to have a BFS traversal of G starting at U. So I must stress that if you want to have it where it examines the entire graph, you're presuming that the graph is connected. That means that there exists at least one path between any pair of vertices. So here's the setup. So what you do is you start off with a queue. So you initialize an empty queue. You have your queue. I'm going to write this one iteratively so that you get an idea of how you could perhaps pursue depth first search in a similar manner. So just to give you a flavor for this. So we enqueue in the starting vertex at our given call. And then we're going to mark it. Now you might ask, Dan, why are we doing that here? It's because we're not going to have any recursive calls, just to be very clear. So we need to make sure we put into the queue at least one element, in this case, at least one vertex, because we're going to have it just simply checking while the queue is not empty. So while there's still a vertex in the queue, as in it's not empty, we're going to do the following. So we're going to do dequeue it. So we're going to dequeue from the queue, and we're going to call that V. And then we're going to, now here is where you would do your processing, by the way. So if you had any like processing, you would do your processing here. So if you have anything you need to do to the vertex at that time, this is where you would do it. And then you go through all your incident edges. So we're going to go through all the incident edges again. And then you just simply check if VW is not labeled, is not labeled, then we check, is W marked or not? Remember, W is the opposing endpoint in this case. So if it is, then you have a cross edge. If it is not, then you know that you have more to add to your queue, right? So if W is marked, then label VW as cross edge. Otherwise, we do three things. First, you label it. You label VW as discovery edge. And then what you do is you're going to enqueue it, and then you're going to mark it. You're going to enqueue W. You're going to mark W. And that concludes the else block. So it's three things here. Just keep in mind the semicolon here. That closes that. Then we would close the for loop here. Then we close the while loop. I'm sort of abusing my space here. But that's BFS. So notice that it's iterative here. I just presented it that way to you. That way you can get a flavor for how you can imagine, say, DFS. Like, if you, keep in mind it's not literally the same, but most certainly it's very similar conceptually. So now let's analyze this algorithm. Okay, let's do this. Let's figure out the time complexity here. So for simplicity, I'm going to presume, as I do here, that the graph is connected. Now, as we had with depth first search, do you remember how I told you that whenever I marked a vertex, I never enqueue in a vertex that is already marked, right? So you know that every vertex is never coming back into that queue, right? It only goes into the queue exactly once. So observe that the algorithm never enqueues a vertex twice. So you're going to see that I'm going to do things a little differently this time. So what I want to do is I want to collect up all of the queue-based operations, and then I'm going to try collecting up all the other work and try to relate it to this while loop here. So I'm going to collect it up into a couple different bins, and we're going to count them separately. So if I were to count up all of the work that happens involving the queues, so like the enqueue operations and the dequeue operations, and down here we also have the enqueues, notice that whenever I give you a vertex, it goes in, it comes out. It never goes back in, right? So all enqueue and dequeue operations take big O of n time, which naturally, when I say big O, I mean big theta n. Because a queue, you can do these operations in constant time. Now you might ask about how BFS does this stuff now. Now this is where we have to be a bit more careful. Because remember, it isn't a recursive algorithm anymore. So far I've accounted for all the stuff that happens with the queues, right? We know the marking here, all these marking operations, they all take constant time. But what about the incident edges? That seems to be a rather interesting part of this that I have not really addressed, right? So for each one of the vertices, notice that for each vertex, I only at once consider all of its incident edges. And each one, I may label edges and mark vertices, right? But I only do it for the incident edges. So really all I have is two pieces to the analysis here. This part and the other part. So the other part is the steps taken. The steps taken compute the incident edges per vertex across all vertices. So the first part is observing that the no vertex is enqueued twice. So you have just the enqueuing, dequeuing taking linear time. Then you have the computation that we see inside of this loop here. So this initialization takes well, it could take at most linear time, right? To do this, depending on which representation you're using. However, we have the question of what happens with this. So we don't have to worry about this. We don't have to worry about that. So everything else here, notice that it's the incident edges, but all of this can be done in constant time, right? So really, we're at the mercy of this. But we have to do it over all the vertices, right? That's the second part here. But here's the beautiful part. We actually already talked about this when we analyzed depth first search, right? So if we consider when the graph is an adjacency matrix, we consider to compute the incident edges takes linear time, right? We do this for each vertex. So that takes quadratic time. So it takes big O of n squared, or big theta of n squared. And of course, when we consider an adjacency list, actually let me note that right here. So an adjacency matrix it's big theta n squared time, where n is the number of vertices. It's just by the very same reasoning we talked about when we talked about depth first search, just the structure is a little different. It's just this combined with that. So in an adjacency matrix, we have to be rather pessimistic because we have to go through the whole row of a row of the matrix. Sorry, I'm getting very excited. However, in the adjacency list, we have the same predicament with the handshaking lemma, right? To compute the incident edges takes big O of the degree of that vertex. In combination with this, where we consider it over all vertices, that's the sum of the degrees, which is still, that's big theta m. So we combine this with linear time plus big theta m. Well, that's just simply big O of n plus m, or big theta m plus m. So this is no different than the results that we obtained with depth first search. Is that neat?